All right, let's get right into it. You know, for pretty much all of history, we've thought of time as this universal river, right? Something that flows the same for everyone and everything once you factor in gravity. But what if that's not the whole story? What if time itself is just a shadow of some deeper reality? Today, we're going to look at a really cool proposal to test that exact idea, and it uses some of the most precise instruments humanity has ever built.
It sounds way too simple, doesn't it? But this question has some seriously profound consequences. This isn't just about telling time. Nope. It's about using the ticks of two different atomic clocks sitting right next to each other to ask a fundamental question. What is the universe actually made of?
And this really gets us to the heart of the conflict. On one side, you've got our current champion, standard physics. It tells us that time is fundamental, it's a basic coordinate of reality, it's just there. But on the other side, you've got this challenger theory, the MMU, which says time isn't fundamental at all. Instead, it's what's called an emergent effect, a projection, kind of like how a three-dimensional object casts a two-dimensional shadow.
So let's really break down these two completely different views of spacetime. You've got the reigning champion, general relativity and quantum theory, and then you've got the up-and-coming challenger, the MMU.
So, standard physics imagines space-time as this perfectly smooth, continuous sheet. You can zoom in on it forever and ever, and it's always just more smooth fabric. But the MMU, it suggests something totally different, that space-time is actually pixelated. It's built from a grid of these incredibly tiny, fundamental geometric units that the theory calls yourselves. So it's not smooth at all. It's a discrete lattice.
And here's what that might actually look like, at least in theory. In this picture, every single point on this grid isn't just a location in space. No, it's a complex little object, an cell, and it has its own internal stuff going on. You can really think of it as the fundamental pixel of reality itself.
Okay, and this leads us to what is easily the MMU's most radical idea. Because if space-time is really built from these fundamental cells, then the thing we experience as time, well, it might not be a fundamental dimension at all. It could be something else entirely.
This whole concept is called the projection principle, and it's really the central rule of the MMU. What it's saying is that all the things we can actually measure in a lab, energy, position, even time, they aren't the real machinery of the universe. They're just the projected effects, the shadows that are cast by that deeper, hidden machinery. So what is this hidden machinery? Well, according to the theory, each one of these cells can basically vibrate or deform in three different ways. Think of them like the fundamental notes that reality can play. There's a mode called W2, and that gives rise to electric phenomena. Then there's W3, which is related to magnetism. And finally, W4, which is a volumetric mode that generates gravity. And here's the wild part. This is how the MMU actually defines time. It's not one thing. It's a specific recipe, a particular mix of those hidden vibrations, W2, W3, and W4. Those alpha numbers in the equation, they basically determine the specific flavor of time that gets projected from that hidden reality into the one we can observe. I know, this all sounds incredibly abstract, right? Almost like science fiction. But here's the kicker. It leads to a very concrete, testable prediction. And the perfect place to run this test is inside a modern atomic clock. So why clocks? Well, it's all about their just insane precision. The best atomic clocks we have today are accurate to 1 part in 10 to the 18. That is so precise, it's like having a clock that wouldn't lose or gain a single second in over 30 billion years. That's more than twice the age of the entire universe. And that is the level of precision you need to maybe, just maybe, see the tiny cracks in our standard model of time, if they're there. Okay, so here's the absolute crucial point. Standard physics says that a clock based on a cesium atom and a clock based on a strontium atom, well, they're both just measuring the exact same universal time. They're just different tools for the same job. But the MMU says, hold on a second. It argues that because these clocks use different types of atoms and different transitions, they are sensitive to a slightly different mixture of those hidden modes. They aren't measuring the same thing. They're measuring different projections of the same underlying reality. And that critical difference is what leads us to a sharp, falsifiable prediction. This is where the theory moves off the chalkboard and right into the laboratory. The experiment itself is actually beautiful in its simplicity. You take two different kinds of atomic clocks and you put them in the exact same spot,
Same place, same time, so they feel the exact same pull of gravity. Then you just let them run. Now we know from general relativity that gravity will slow them both down by the same amount. So you do the math and you subtract that shared effect. The big question is, after you've done all that, is there anything left over?
And that's what makes this such a powerful idea. It's what scientists get really excited about. They call it a null versus non-null test. All that means is the result is either 0 or it's not 0. There's no gray area, no ambiguity.
So let's just lay it all out. Here are the two possible outcomes, plain and simple. Standard physics, which is built on this idea of universal time, absolutely demands that this leftover difference, this differential residual, must be exactly 0. No wiggle room. The two clocks have to agree perfectly once you account for gravity. But the MMU, it predicts that because the clocks are different projections, that leftover number can be non-zero. And finding even a tiny measurable disagreement would be the smoking gun.
So what are the stakes here? I mean, why does this one little measurement matter so much?
Well, this test is just so powerful because it's incredibly clean. By putting the clocks in the same exact spot, you cancel out all the common noise. And by using different atoms, you're specifically asking if their internal physics connects to spacetime in a different way. Finding any residual, no matter how tiny, would be a direct signal of new physics. It's a straight-up yes or no vote on the MMU's biggest claim, that time is a projection.
And so we come right back to where we started, back to this foundational, mind-bending idea that what we experience as the steady, universal flow of time is actually the complex result of hidden vibrations within the geometric building blocks of space-time itself. So the ultimate question is still out there, but it's a question that might soon be answered, not by a philosopher, but in a laboratory. Is time a fundamental feature of our universe, like we've always believed? Or is it an emergent shadow, just hinting at a reality that's far deeper and far stranger than we ever imagined? The clocks are ticking.